Basically, like, why do I care to talk about d-dimensional unitaries? It's just because I was just trying to find the laziest possible way of understanding how to construct them. And of course, the laziest possible way is to construct them out of smaller ones. You need to do, like you need, in addition to d minus 1 unitaries, you need a smaller bit also. Now, it turns out that I'm interested in more than factoring unitaries. I'm also interested in measure, like understanding the distribution of these unitaries. And what's the laziest way of understanding this distribution? It's to understand it in terms of the previous ones. And that matches really well with the first item. And then what is the laziest possible way of averaging over these unitaries? Well, it turns out it has nothing to do with the d minus 1. So that part is pretty slick as well. It uses something called Weingarten functions or Weingarten functions. And so these three lead me, like these three motivations, they pipe into the three promises for the talk. Hopefully, a nice recursive method of constructing d-dimensional unitaries, a nice recursive method of understanding the measure, the distribution of these unitaries, and a nice way of doing averaging. Okay, so we've seen it, this morning there was a bunch of these diagrams with boxes. Okay, of course the one I like best is the first one. But it turns out, and in fact, there was somebody this morning who basically had exactly the same scheme. I think the colors were different. But it's not the only one, it's not the first one. So maybe the most famous one is by Reck et al., 1994. Now, it turns out that the scheme that is there, so two here is a beam splitter and a phase shifter. And here you have a bunch of phases at the end, right? So it turns out this is really brilliant. It looks like they did not know this work by Hurwitz, 1897, but they came up with this optical implementation of this. And Reck et al., they cite instead Murnaghan, who kind of rediscovered the work by Hurwitz. And I think this is a really nice paper. You should read it. It's very, very nice. So there's another one, which is due to Clemens. And it doesn't work on this kind of triangular array. Like this one is kind of have this sort of interleaved system of boxes here. And they have a reason for doing this. It has a smaller depth, so it's better if you're worried about losses. They give a really good argument as to why you should use that one in some instances there. So you can look up that one as well. Now, the one I know best started with this one. I guess, right? It's like I didn't steal this from the previous speakers. It's just a natural way of doing this. So the BCS there is Barry Sanders. And so this morning I was going to thank him for putting up with me for 25 years. But now I learned that you put up with me for 25 years also. So I guess it goes both ways. And the idea here is you're going to take a U3, you're going to split off a phase, and you're left with an SU3. And what I want to do is I want to convince you that you can break this into boxes that connect neighboring wires or neighboring atoms or neighboring QuDits or whatever else. And the key point is some of the boxes have 3 parameters and some of the boxes have 2 parameters. Okay? I don't have to do it that way, but here's an example of where I take this SU3 and I just break it in terms of SU2s. Just to establish some facts here, like the 3 boxes, they look like this. So there's 2 phases, in a ratio like this, and they correspond in the usual way to this kind of stuff here. And the 2 box, the first and the last angle are the same. So it depends on only 2 parameters. Okay, so you just have to remember the 3 boxes depend on 3 angles, and the 2 boxes depend on only two angles. And just this one time, I'm just going to show you how you get to that thing here. You start with some unitary like this. It's an SU3 one. And the idea is you're going to take, this is a 3 box here, has this form. The y and the z are completely determined by the entries in the first column. And the y and the z's, in general, they're complex numbers. So I really have 2 phases here, each for one of the entries. And I have a splitting ratio. And if I multiply u1 by m, which I denote by this box, seeing this thing here, the entries are designed so that there's a 0 that appears there. Okay? And then what's cute is you're left with a real number on that thing here, and x. X is some complex number. And of course, the sum x squared plus y squared plus z squared must be 1 because it's unitary. So I can write it in this way. And then I write this 2 by 2 block here. Now, the key point is now it depends on 2, not 3 parameters, because one of these is a real number. I can write it in this way. And then the U3 and the U2 acting on this, they give me a 0 here and here. And because everything along, like down a row and across, down a column and across a row must sum to 1. If I get a 0 here and a 0 here, I must also have 0 there. And I'm left with another SU2. And so that's it. You just take the inverse of U3, U2, U1, and that's how you break it up into bits and pieces. Okay, so that's super simple to do. Okay, so now the idea is, and I think somebody was asking, why do I break it up into 2 by 2 boxes? Well, what I'm going to do here is I'm actually going to break it up into an SU. Again, I take out a phase, so I get an SU4 here. I break it up into an SU3 part and another SU3 part and something in the middle. Okay? And that SU3 here, that SU2 there, you can see the wires connected directly to this other one, and it's unimpeded by this 2 box. So I can just slide it across. I've just done that here. And that's a full SU3 block. That's a partial SU3 block, and there's something here, which is a 2 block, which looks exactly like the 2 blocks I wrote before. So 3, 3, 3, so that's 9. 1, 2, 3 plus 6 is equal to 15. I have the right number of parameters when I throw in the phase. And I think somebody just showed basically that one. I think you can see it if I write it in this way. That's exactly the one you showed, right? Maybe the colors were different, but that's about it, right? Okay, so kudos here to Olivia Di Matteo, who's an alumni from IQC. Some of you who are from IQC remember her, and Luis. Okay, so that's easy enough. Turns out I can do the same with U5. Just split off a phase. And I wrote the part in the middle that connects wires 4 and 5. And then 2 SU4 pieces that connect wires 1, 2, 3, and 4. And now you see there's a yellow part on the left side. There's a 3, a 2, and a 3. I can slide that whole thing across on the other side there, because it slides smoothly under that 2 box. So this acts on wires 1, 2, and 3. This acts on wire 4 and 5, so these guys commute. I can just put them on the other side. And I'm now left with that structure. And that's it, basically. You can just keep on going. If you're interested in finding exactly what these things look like, you just use exactly the same algorithm as for the U3 one. The first one is a 3 box because I have 2 complex numbers and a splitting ratio. Then I generate a real number, so the next one will be a 2 box, and then another 2 box, another 2 box along that spine there. And then I'm left with an SU, here it's an SU4. I just redo it again. And So you can see the 3s are all at the bottoms, and everything else is just a bunch of 2s. And that's as hard as it gets. You can do that for SU10, SU20, whatever else. And in fact, there's a Python code on the Penny Lane site. The Zenit, like Penny Lane has a Python implementation. It's the most recent one, and Olivia wrote the original code, and we tested it up to 17. It's bug-free. Okay, so this works. Now, the interesting piece is I can heave off some parts on the right if I want. I can heave off some parts on the left. So Barry was mentioning, he was talking about like dividing out here. Maybe, I don't know, for some reason you're interested in just throwing away some blocks. You can just do it that way. Like there are ways of organizing various blocks, sliding them across as long as they don't bump one into another. It's just pretty simple. Okay, so that's the nice part. Okay, so hopefully that was a nice recursive method for constructing d-dimensional unitaries. If you don't want to break it up into break it up all the way into 2x2 boxes, you can still take an SU3 part, and stick something in the middle, and then it will work. It will give you like an SU4. Counting parameters becomes a little harder, but it's okay. It's doable. Okay, so let me now talk about the Haar measure. So there are many instances where you're interested in averaging. I mean, if you think of average complexity of circuits and all that sort of stuff, right? Like you would want to average over ginormous matrices. And maybe you're also interested in understanding the distribution of angles, because they don't have the same, they're not necessarily uniformly distributed. And the tools to do that is this what's called a Haar measure. I mean, because I'm interested in averaging, I'm just going to talk about this in the context of averaging, but there's various applications, barren plateaus, and that kind of stuff here. Now, the simplest example is the one you know from spherical harmonics, right? If you want to integrate something like this, you have to put in this factor. If you're a good undergraduate, you put in this factor. If you're a bad undergraduate, you forget about it, and you get nonsense. Okay, so that's an example of this is the Haar measure on the sphere. And now, of course, I'm going to talk about d-dimensional unitaries. I'm not going to put in the the differentials of all the angles, because I would have to write 15 or 16 or some huge number. I'm just going to concentrate on how you can get this factor of sine theta for each of the steps in each of the boxes in my scheme to write a unitary. So I should tell you, there's an algorithm to compute this. Like you take the determinant of something, okay? Now, the size of the matrices, it grows quadratically, but it's not that hard, actually. I mean, it's reasonably easy. It's basically something like this, and I wrote a differential here, and why is that? Is that because, like the Haar measure, it's basically unique, but of course, if you write it in different coordinate system, it will look different in the same way that you can talk about properties of a vector. But if you write the components in spherical or Cartesian coordinate, the components are going to look different. It's still a vector. You can still make sense of a bunch of properties of it. So why is it invariant? Well, if I just multiply my u by some arbitrary u naught on the left, I just plug that in, and of course the inverse makes the u1 appear on this side, and because it's constant, so these guys basically cancel out, and I'm left there. So I could multiply my unitaries by anything on the left, any constant matrix on the left. I can do it with any constant matrix on the right also. It's not going to change anything, right? It doesn't change any of the properties of the measure. Okay, so again, what is the laziest way of understanding the distribution for a D by D matrix? Well, I just told you that I take my D by D matrix and I break it off into D minus 1 pieces. So I write, right? So I have the determinant of A times B, where B is the part, all the blocks on the right, the determinant factors. So this measure here, it breaks up into a part that I already know, the D minus 1, and then a part that I don't quite know. Well, it turns out that the part I don't quite know, I actually already know quite a bit about it. Let me tell you a bit about that. So the part, that part here, that should be a SU, but that's okay. It's the part on the spine that runs at the leftmost of that set of block. And in fact, that spine does have a structure. And then that guy here is the part on the blocks on the right. Now, the spine breaks up more. And I gave you a hint as to why, right? It's because, right, this thing here is basically an SU3 transformation, except that I removed the box. I moved it towards the right. So the measure here is going to be an SU3 measure with some piece taken out. And that's the piece that corresponds to the block I removed. So let me show you what this looks like. I took SU4 just because it's sufficiently simple. OK, so that part here, I took out the U1. So that's for this part like this. That's what the SU3 measure looks like. That's what the distribution of angles looks like here. Now I have the part for the spine, for the part of the spine that is on the left. And notice it's exactly the same form, but there's a piece missing, and that's the box that's missing that I moved under. And there's a part in the middle. And the part in the middle is the new part. And it turns out that it computes easily for this specific example. It's this fourth power of some angle that multiplies the angle here. So that's pretty simple. If I have to construct the distribution on U5, I'm going to have an SU4 part. Then I'm going to have an SU4 parts with a bunch of blocks missing. And this piece in the middle, the only thing that changes is the exponent. So that part there, the part that is associated with the two boxes, it's some power of sign like this. And K here is for mixing wires K and K minus 1. The part for the part of the measure for the blue box, like the 3 box, just a sign. And in fact, if you remember, the blue boxes, they mix wires 0 and 1, like 0, 1, and 2, so K is equal to 2. If I put K equal to 2 here, that piece disappears, and I'm left with that. So there's like super nothing terribly new here. I just take this, and I just repeat it for every one of my blocks as I go along. And you can remember that for the 2 blocks. And for the 3 blocks, it collapses to this simpler expression. Now, what's interesting is that the measure concentrates. So what I mean by this is as follows. As I go higher up the spine, I pick up a larger and larger factor of this sine factor here of half the angle. So here's an example for K is equal to 20. Here's an example for k equals 4. So in practice, what that means is that for k equals 20, this splitting angle beta, which determines the ratio of the of your wire 20 to 20 to 19, I mean, it really wants to be close to pi. And this actually thins out as well. As opposed to k is equal to 4, it's actually wider. If you have the expression, so like the most probable angle is actually easy to find. And there's also an average value of the angle, which can be computed. It's an ugly mess. It has factorials. But there's an expression for it. Okay? It's not like you just basically, like you just need to be good at integrating powers of that sort of stuff. And the factorials come out essentially when you expand this into exponentials. So again, messy, but like too messy to write, but just basically it exists. And I've checked 2 of my boxes. So I hope thus far I have convinced you that I can easily construct D by D matrices. I can easily understand the distribution of the angles. And now I'm going to talk about averaging. Now, there are many circumstances where averaging is really interesting for a variety of reasons. And I needed a simple example. So imagine the QuDits state that is given here. So I took it to be diagonal because I didn't want to have so many indices going around. So I just imagine a density matrix. It looks like this. Right? I think the notation is it's fairly standard. And what I'm going to do is I'm going to ask the question, what is the average state that comes out? So suppose I pull out a unitary at random, a D by D unitary at random, and I just apply it to this stuff. What comes out on average? I need to find an expression like this. Of course, because I have 2 QuDits, I'm going to have 2 helpings of the unitaries, one for each qubit. Once for each QuDit, I should say. So when you spread this out, you get a bit like you get these coefficients here, which come from the initial state, and then this QuDit I, it goes all over the place to a linear combination of alpha. The J1 goes like this, and you pick up a bunch of matrix elements that are entries in the unitary. This is a D by D unitary. And so the averaging means averaging over that kind of stuff there. Okay? So it turns out that this was a fairly hard problem until about, 10, 15 years ago. Now, if you're interested, there's a complete answer, which not only is averaging over the unitaries, but also if you have orthogonal transformations, symplectic transformations, in this paper by Benoit Collins and Piotr Sniady. And that paper is like a real tour de force, but it's not for the faint at heart. Okay. So this was the thesis of Benoit Collins, and then he had some bugs, and he fixed that with Sniady. If you're interested in a much, much more intuitive approach, I recommend you go. So Pierre Melot is, of course, it's the same answer at the end. But he was working on disordered media, and he just basically did it in a way that is maybe a little more approachable for mere mortals like me. Anyways, I got a lot out of that one. So it turns out the averaging does away with a huge amount of information. And it's extensively based on the invariance of the measure. I'm not going to give you lots of examples about this. You can look up the paper by, yes? Yep, you can look up the paper by Pierre Melot. And here's an example. So here I just give you A, B, C, D, E, E, and F. I put them in red because they're the first indices. I want to distinguish them from the black ones, which are the second indices. So I'm going to, by the way, if you don't have as many U's as you U daggers, it's automatically 0. Okay? So I construct two arrays, the red one and the black one. And the answer depends on finding shuffles, permutations of the bottom row of this one that will take it to the top row, and the bottom row of this one that will take it to the top row. And then once you have found this set here and this other set, you make a sum of these objects that are called a Weingarten function. So here's an example I specialized like this. So I have the array ABA, BAA, I like this. So you can see that if I shuffle the first and if I permute the first and second entry at the bottom, I get the top one. So P12 is in. And P123, which sends the first to the second to the third, and the third back to the one, it's also in. And likewise here, the taus, I can do nothing, the identity, and I can permute 1 and 3. So I have my set of sigmas, my set of taus, and I just put that in here. It's a sum of 4. I got 2 here and 2 here. And the answer by magic comes out to something like this. It depends on D only. It doesn't depend on D minus 1. And all the information about the actual numbering, so it doesn't matter if A is 1, 2, 3 or whatever, or B is 1, 2, 3 or whatever else. The only thing that matters is the connection between the top and the bottom row through these permutations. Okay, so just I'm nearing the end here. So that's the pretty formidable expression found by Collins. And thankfully, there was a student who wrote a Python code for it. It actually works. He did actually also a little more. So it's actually very nice. And I gave him a mathematical implementation. And I think, again, I should tell you that I had a student who did his PhD at Perimeter, who actually, like that part here, that part in red is really hard, it's like hard to compute. So I had an undergraduate student to do that. It was like really interesting. So the hard part is to find these sigmas and taus. And believe me, this is a substantially easier way of computing averages than if you try to integrate the trigonometric functions, because you end up with super oscillatory functions, and it's like hard. And moreover, you get an answer in terms of D, and the asymptotes for really large D, the answers are known, what these functions look like. So it's just a job of finding these things. And there's also all kinds of ways of getting approximate answers here. You can work that out as the inverse of a matrix. You're constructing using graphs, and that inverse can easily be iterated. Okay, so I'm closing to the end. Of course, like I could put, instead of sliding my blocks to the right, I could slide them to the left. Wouldn't make any difference. Then the measure would factor on the left instead of factoring on the right. I can do it upside down. You can play games with moving boxes around. It's actually, like once you understand that you can slide boxes if there's nothing in between to interfere, if they're connected by 2 uninterrupted wires, it's actually pretty simple. So I'm done with my 3 promises. I did hope present a nice way of constructing D-dimensional matrices. I told you a bit about the Haar measure. I told you a bit about averaging over unitaries. And the last thing is to thank the people who funded this work, and CERC and ACFAS. Thank you.